In this video, I'd like to revisit the fundamental theorem of calculus, as well as talk about the U substitution method for determining integrals. We talked about this area function, a of x, as a way to measure accumulated change, or at least I tried to stress that in class a fair amount. And what I'm trying to clarify here is that if I've got a function that looks something like this, and if I had some arbitrary ending point and starting point, let's say that this is a, the starting point of the integral, and x is the ending position of that integral. Let's keep in mind that this position x is a variable, so it could be anywhere. Imagine this line sliding to the left or to the right. Well, if x was positioned right here and we were to measure the area underneath this curve, this of course gives us the amount that of accumulated change, if you will, from A to X. If I started with this amount of something and started accumulating more and more of it, the grand total of stuff that I end with is equivalent to the area underneath this curve. Now, as X slides farther to the right, we should notice that the area is continuing to accumulate. The total area underneath this curve is growing. But as we mentioned in class, is that when we start accumulating area beneath the x-axis, that actually counts as negative area, and that concept is a bit strange. Clearly the area itself doesn't go negative. You can't have a negative area measurement, but the value associated with this becomes negative. And the reason why we say that that is a negative area is because the amount of growth or the amount of change that's being accumulated at this point starts to decrease. So while the area, while the stuff, if you will, is being accumulated in this position with positive x values, when the y values, when the y values become negative, the amount of stuff we've accumulated starts to decrease, and the amount of stuff that we lose due to this decrease is equivalent to the amount of area that's associated down here. And so that's why this area is considered negative, because this amount of stuff associated with this area is subtracting from the amount of stuff that's associated with this positive area. And so when we start talking about the derivative of this area function, we need to convince ourselves to stop thinking about slopes for just a second, because the derivative of the area function is not tied to how steep the curve is, but instead it's tied to the rate at which the change is accumulating. So the rate of change in area. So how does the area change? Well, again, the area is getting larger here through the rest of this graph while the function is above the x-axis, but the area accumulation starts to decrease as the function falls below the y-axis. So again, we're accumulating more and more and more stuff here, and then as we switch over down here, we start losing stuff. So area is increasing to this point, and then it decreases starting at this position. Now what you may also notice is that because this function itself is decreasing, the rate at which the area is growing is much slower at this position, right? As the height of that function drops, the amount of extra area that we accumulate grows at a shorter or a smaller rate. And so by learning the second form of this fundamental theorem of calculus, we tend to not notice how the derivative of the area function is actually quite easy to compute in many cases. So let me slide this out of the way here, and I'll just really clarify something here. If our area function, a of x, is defined as the integral from some arbitrary starting point, some fixed starting point a, to some variable x of another function who's describing the height of the graph. Right? If this is the area function, then when we take the derivative of that area function, we're simply asking you to find the derivative relative to x of this integral. And so by extension of the fundamental theorem, down here we are saying that the derivative of an antiderivative is simply the function on the interior. So the derivative of the antiderivative of a function is that function itself. And the antiderivative, the derivative of the antiderivative is the function relative to x here, because x is the variable in this area function. T is no longer the variable. T was used to describe the shape of the graph, but x is the variable on which we would compute the area or accumulated change function. So if I were to look at a specific example down here, I don't know the function that was used to create this shape, but the function that's shown here is f of t. We have a t-axis and a y-axis, so the y components of the coordinate are equal to the function evaluated at t. The letter x is being used to give us some sort of right-hand endpoint to this accumulated change function. We're starting at an x value of 1. I think we all recognize that. The g of x is going to be the area function, where the area underneath f is computed, starting at 1 and moving upward towards x. So x could be here, x could be here, x could be anywhere along this right-hand side. X is a variable that can be moved to any position. And that technically it could be moved to the left of 1 as well, but we'll try to focus on the positive side for right now. And part of our instructions do limit the function's domain to x values that are between -2 and +4. So it's not going to go beyond that range. So if we're being asked to calculate g at 1, well, that's the same as the area function at 1, right? We want to find the area underneath the curve. They're just using the letter g here instead of a. Well, if my integral was written, 1 was our lower boundary of f of t with respect to t, and we integrate from an x value of 1, a t value of 1 to a t value of 1, well, the area underneath the curve right at this position with no width, right, there's no horizontal distance between 1 and 1, the area, of course, has to be equal to 0. For g to be evaluated at 4, that's this integral from 1 to 4 now of the function f of t dt. We don't know what this function is, so it's not like we can use the antiderivative to compute this result. We are calculating these results based on area formulas. But now we're talking about the accumulated change from 1 to 4. And now here again, as we start at 0 and think about all of the area that's associated with this graph as we move to the right, we are building more and more area. We are collecting more and more stuff. Now we're collecting it slowly here because the amount of stuff on this very short end of the graph does not grow very quickly at all. But we are still accumulating stuff. That's why this area is considered positive. But as we get to this point on the right side, we start losing some of our stuff because the area that we're calculating now is underneath the x-axis. We actually start losing stuff. So imagine, if you will, that this function f of t was representing how fast we were moving in a car based on the time t. If t is positive, the amount of distance that we are away from our starting point is growing. Now, we may have been growing very, very quickly at the beginning. We were increasing at 4 units at the beginning, and then we were increasing by 1 unit at unit 2 here, and then we were increasing just a little bit and a little bit more, and then till ultimately we start losing value. When we have a f of t result that's negative, that actually means that our direction is decreasing and we're moving back at a faster and faster rate. And so we might be interested in the total distance that we are from our starting point. And if we make it to the end of our journey and turn around and start coming back, well, the total distance from start to end is a little bit less than the distance originally. And so while this rightward direction might have been the area associated with this positive number, this leftward direction would be the area associated with this negative number or negative position. And so with a little bit of mental math, we might recognize that the area associated with this triangle is equal to -1/2. And for this upper region, well, we've got a positive 1/2 here. We've got half of 3 here, 3/2, half of the base times the height. And then we've got an area equal to 1 square unit here. So if we have 1 plus 1/2 plus 3/2, that's 6/2, or a total area equal to 2 units. So 2 units for the upper area minus 1/2 of a unit leaves us with 1.5 units. And 1.5 could also be written as 3/2. So 3/2 of a unit will be the result for g of 4. Now g evaluated at -2, keep in mind that our accumulated change starts at 1 and now is moving backwards towards 2. So if we're starting at 1 and we move backwards towards 2, think about it this way. If we had started at 2, and this was our, say, rate of travel again, the speed that we're moving, as we're speeding up, moving from left to right, clearly we are moving a further distance from our starting point. We're speeding up and we're moving away from our starting point. But if we talk about traveling from 1 backwards to -2, we're not speeding up along the way. We're actually reducing our speed. Each of these data points indicates a loss of speed or velocity. And as we lose speed, the rate at which we accumulate change decreases. But it also implies that we're not moving forward, but instead moving backwards. And that's where this negative result is going to come into play. So the integral starting at 1 and moving backwards to -2 is directly related to the area underneath this curve, which in this case, let's see, we've got a base of 3 and a height of 4, so that's 12. Divide that by 2, and it looks like the area associated with that triangle is equal to 6. But again, because we're accumulating change backwards, we're going to report this as -6. And essentially, we've lost 6 units of stuff. If we were talking about motion, we are now 6 units leftward from where we began. So to answer the following question, this is the one that I think caught a fair amount of students off guard when we saw this on our exam. Calculating g prime at 1, what is the rate of change of the area function when the function reaches this position? Well, how is the area changing? Not how the function itself is changing. We're not particularly interested in the change of the function's behavior. In fact, this is not differentiable. The function itself is not. But think about the area and how it changes precisely at this position. Well, pretend for a second that the function itself actually stayed level for a moment. Let's not let it decrease like this. If it stayed level, and I tried calculating the area, how much area have we changed between second 1 and second 2, the time 1 and time 2? Well, the amount of area that we've just gained in that interval is 1, 2, 3, 4 units. It's grown by 4 units. And so what our antiderivative rule of accumulated change is telling us is that if I want to know the derivative at this particular point, all I need to do is evaluate the function at that particular value. And that's good at either endpoint, a to b, from our lower boundary to our upper boundary of that integral. So precisely at this position, at this moment in time, the area is growing by 4 units because f evaluated at 1 is equal to 4. G prime at 1 is equal to the f function evaluated at 1, which in this case is equal to 4. Precisely at that moment, the graph is growing by 4 units per unit of, let's say, time, if t stands for time. Now, if we were to move a little bit farther along, because the function itself is decreasing, well, the area is not accumulating nearly as much over here, and at this point it's only growing by 1 unit per unit of time. And down here, the area is not accumulating anymore at all. f evaluated at 3 is equal to 0, so therefore our area function evaluated at 3, its rate of change, is just 0 as well. So the area is not accumulating anymore at this precise instant. In fact, we were noticing that the area was increasing up until this point, and then it begins to decrease at this point. And when we change from an increasing value to a decreasing value, we've stumbled upon a maximum unit, or a maximum point of that graph. And so that's exactly what's happening here. At what value does the function g have a minimum or a maximum point? Well, we should recognize, following our conversation today, that while the function is increasing here and is positive, an area is continuing to accumulate in a positive sense. But as soon as we switch over to this position here, area begins to accumulate in a negative sense. And while the area values were growing all through this region, the area values begin to decrease in this region, and therefore we have found a maximum point right here when when t is equal to 3. And so I would say something like this: at time equals 3, a maximum of g of x occurs, and that's because, or since, the sign of g prime of x changes from positive to negative. And g prime, of course, is just the result of f. Right? F is positive, positive, positive. It switches to negative, and that's where our area starts to decrease. So I hope that clarifies a couple things with the fundamental theorem of calculus and how it affects accumulated change. I think I'll stop the video here and create a second one for these U substitution examples, and we'll also continue to discuss these in class next week.